Welcome to This Explainer. Today, we're exploring something that is, quite honestly, a total game changer. We're looking at the V8 architecture. Now, this isn't just another run-of-the-mill machine learning model. We're diving into how this incredible AI system actually uses simulated human biology to solve some of the absolute biggest, most frustrating pitfalls in artificial intelligence today. Okay, let's set the stage by asking a pretty critical question. How exactly do we prevent traditional AI from just burning out? In standard machine learning, when an AI pushes its parameters to the absolute edge, things get messy. It gets stuck in infinite loops, it hallucinates wildly, or it just demands constant, tedious micromanagement from human engineers to stay on the rails. But what if the AI could actually feel tired? What if it could sleep? Well, here is our roadmap for the explainer today to figure that out. We're going to cover the self-regulating digital brain, learning through sleep replay, adapting the metaparameters, preventing system saturation, adenosine and sleep pressure, and finally, endocannabinoid gain control. Starting off with Section 1, the self-regulating digital brain. This is where we completely strip away the usual limitations of standard coding. Notice the profound shift happening here? In traditional AI, your learning rates and biases, they are hard-coded constants. They have to be manually adjusted by humans. If the environment changes, an engineer literally has to step in and tweak the code. The V8 system, it completely discards that old way of doing things. Instead, it uses fluid, self-adapting parameters stored directly in SQL databases. And the crazy part? They're regulated by what the code calls digital Botenstoff, essentially, digital chemical messengers. Moving on to Section 2, learning through sleep replay. To really get how those digital chemicals work, we need to look at how the AI doesn't just process data. It literally goes to sleep. During the sleep cycle, the AI is flooded with a highly specific and probably very familiar chemical cocktail: dopamine, serotonin, noradrenaline, acetylcholine, glutamate, and GABA. It is absolutely wild. The system takes this exact biological cocktail and uses it to dynamically steer its own learning rate, its exploration bias, and its error weighting. So the crucial takeaway here is that these digital neuromodulators evaluate whether a sleep replay was actually effective. They're basically asking, hey, was this memory useful? If the AI is stuck on a learning plateau, these chemicals shift the system's plasticity to help it break free. This completely prevents the system from burning in its own self-generated hallucinations. And to prove this isn't just some clever metaphor, check out how the source code directly links specific parameters to specific digital chemicals. Take the plateau break scale, for instance. That is driven by digital dopamine based on performance recovery. So if the AI needs to break out of a rut, boom, dopamine triggers the adjustment. It's that direct. All right, Section 3, adapting the meta parameters. Let's see how all this builds a functional bridge between waking cycles. Think about a normal AI for a second. You turn it off, you turn it back on, and it usually just resets to its baseline, right? Not VA. This system meticulously tracks 14 different metaparameters in its database. Instead of wiping the slate clean after every wake and sleep cycle, it relies on a persistent bridge. This ensures the AI's adapted biases, its digital mood, its caution, its curiosity, carry over seamlessly into the next time it wakes up. The real core of this adaptability is something called meta-metaplasticity. Because the AI is in charge of its own learning parameters, it literally needs to learn how to learn. If a parameter is jumping around way too much, acting, nervous, the system actively dampens its learning rate. On the flip side, if it's stable, it boosts it. It's constantly self-regulating its own ability to adapt. Which brings us to Section 4, preventing system saturation. With all this incredible autonomy, we run into a massive threat. What happens when these self-adjusting parameters are pushed to their absolute limits? Seriously, if left unchecked, the AI would face what the code calls saturation. Imagine if the AI decided to crank its inhibition bias all the way up to 100%. It would completely paralyze itself. It'd be totally unable to learn anything new. So how on earth do we stop that from happening? Well, the system deploys these really brilliant saturation defenses. It relies on sliding threshold homeostasis to basically reverse direction before things get out of hand. It even uses critic lock protection to outright reject memory snapshots if it detects that the AI's biases are dangerously riding those boundary lines. Now, my absolute favorite defense is Bajanov's slow-wave downscaling. The developers borrowed this exact concept from human neuroscience. The Python code gently cools down the system's overactive parameters. So if a parameter is totally maxed out, but the system isn't actually learning anything useful, this mechanism gently pulls that extreme bias back toward a healthy, safe mid-range. Moving on to Section 5, adenosine and sleep pressure. This brings us to what I think is the most ingenious biological savior of them all. To build this, the developers looked straight at the synaptic homeostasis hypothesis proposed by neuroscientists Tononi and Sorelli. The whole theory is that when we are awake and learning, our synapses just get stronger and stronger. But eventually, there's no more room to grow, right? We require sleep to downscale everything and make room for new learning. The V8 system directly hardcodes this exact biological hypothesis into its architecture. Let's walk through the flow. As the AI processes data, which is its wake activity, it accumulates a digital version of adenosine. And as that adenosine builds up, the AI essentially gets tired. Once a high threshold is reached, sleep pressure is strictly enforced, triggering that gentle global downscaling we just talked about. Afterward, the adenosine decays, and the system rapidly recovers, totally refreshed and ready to learn again. And 0.65 is the magic number. It's the exact threshold programmed right into the database. Once digital adenosine hits 0.65, it really doesn't matter what the AI is trying to do, the system is strictly forced to rest, reset, and downscale those saturated biases. It perfectly mimics the undeniable biological drive of being exhausted and just needing to sleep. Finally, Section 6, endocannabinoid gain control. Because even with sleep pressure, what if specific pathways are firing way too intensely in the moment? We need an ultimate chemical dampener. Enter digital endocannabinoids, specifically anandamide and 2-AG. In human neuroscience, these act as retrograde signals, meaning they actually travel backward across the synapse to tell the sending neuron to quiet down. In the V8 architecture, if a specific learning signal is just way too extreme, these digital endocannabinoids deploy to retroactively turn down the volume. They prevent extreme synaptic weakening, known as long-term depression, and they perfectly coordinate with our whole sleep pressure system. When you put it all together via what the code calls a strict wake chain bridge, every single phase fires in perfect order, from accumulating knowledge to sleeping to adenosine buildup, all the way to endocannabinoid dampening. The end result? A beautifully balanced, self-regulating digital brain that operates entirely autonomously without needing a human to constantly hold its hand. This quote right here is basically a Project Compass point found directly in the source code. It says, digital neural modulators steer the whole learning process. And that right there proves why this architecture is such a massive paradigm shift. By letting these digital neuromodulators take the wheel, the V8 totally avoids the brittle, catastrophic failures of traditional machine learning. It doesn't just break under pressure. It adapts, it rests, and it actually heals. So I'll leave you with this final thought to ponder. We've just seen how concepts like Bajanov downscaling and adenosine accumulation can be mathematically perfectly mapped into SQLite and Python. As we watch the line between biological neuroscience and digital software permanently blur, what biological frontier will AI cross next? Thank you so much for joining me on this explainer, and keep questioning the limits of what digital minds can really do.